Good morning, everyone. Today I am going to explain about predicting weather state using hidden Markov model. Here I will explain programmatically with a hidden Markov model based on the weather prediction. So a probability is applied to sequential prediction with hidden state. Understanding hidden Markov model. Hidden Markov models are probability framework designed for sequential data analysis where the system true states remain hidden for direct observation. We can only see the output generated by the hidden state, creating a layered prediction challenge. In this weather prediction project, we use an HMM to determine whether conditions are sunny or rainy based on sensor observation. The model learned pattern between hidden weather states and observable measurement enable us to interpret the most likely weather sequence. The problem we are solving. The objective. Given an observed sensor sequence, determine the most likely underlying weather state that predict those observations. For the our observed data, for sequence um, in the array 1, 1, 1, 0, 1. So each value represents a simplified sensor reading. For example, 1 might indicate high temperature, um, humidity, conducive to cutting condition, while 0 indicates low reading. As our components explain. So hidden shade. There are two we are going to predict sunny and rainy. And then the transmission matrix. So with the transmission matrix 0.7, 0.8, 0.4 and 0.8. It is a probability of weather changing between states. So from this state to this state, like probabilities have one. So we will separate the two states. So these are the states we are changing. Emission matrix and 0.1, 0.9, 0.8, 0.2. Probability of sensor output given current weather. Initial probability 0.5 and 0.5. So we have to initialize value. So then only we can able to iterate the value of transition matrix and emission matrix to find the sunny and rainy probability. It is the initial probability we actually calculate in for equal likelihood of starting state. So here it is a program implementation explanation here going to explain it. So Python implementation with NumPy. So the algorithm follows a structure approach to compute probability for the observed sequence. Initial alpha matrix. Set a probability distribution of each state at time t equal to 0. Compute forward probability. Recursively calculate probability through the observation sequence using transition and emission matrices. Calculate total probability. Sum final probability to determine likelihood of the complete observation sequence. 4. Decode state sequence. Track back through probability to identify the most likely weather state at each time step. So this is the program implementation I have done. So first I input the NumPy library and then I initialize accelerated transition matrix, emission matrix, initial probabilities and observed sequence. After that we will iterating. So we calculating the alpha with importing the np.0 with the observed sequence and the initial probability. So we will get an initial state. So after that we have to calculate the first row of the alpha matrix. So within the first row, means it is many row with letter. So first row we have to initialize. So this is like we have to initialize. So initial probability into emission within the array from this array to observed sequence. For t in range, we use two for loop, the nested for loop. So with the observed sequence and the initial probability limit. So with that we will again and again alpha will strain with multiplying with the emission matrix, observed sequence and the transition matrix. So finally we will calculate the probability after completing the nested for loop with the sum NP reference, the total sum of the alpha value that we got. The probability of the observed sequences we will get the probability. So I will show the output. A mostly likely sequence we will initialize in a list. So from this for loop you will observe sequence if alpha t comma 0 greater than alpha t comma 1, which is have a highest value, it will give the sunny and rainy value. If it is and 0 greater than a t value greater than the alpha of t t of 1, it will give the sunny or else rainy. So the most likely sequence is, so which is the most likely sequence, what sunny or rainy, it will got an output. The probability of this sequence is 0.024. We got it. The most likely sequence of weather states is sunny, 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 rainy, rainy, sunny. So these are the probabilities we have got it. Next, result and interpretation. Key finding. The observed sequence has a probability of 0.024, probability 2.41. Under this as mm. Predicted weather sequence. We got this sequence. That the model reveals a clear pattern. The sequence begins with a predominantly sunny condition, transition to a rainy period in the middle, then return to sunny weather. The transition pattern measures the observed sensor data well, demonstrating how the HMM successfully interferes hidden state from observable evidence. Trace transition with its visualization diagram. The diagram illustrates how the model transition between weather states. So, for the sunny, I got 70 to 30%. Uh, for the rainy, we got sunny to stay, so 40 to 60%. In the weather Markov model, two strange probability, so the sunny and rainy. So, from this state to this probability of percentage we have got. Next, this is most important, the real world application as HMM. So, weather forecasting. Predict future weather states and appropriate pattern from historical observable and sensors. Speech recognition. Map continuous audio sequence to discrete phonemes and words by natural language processing system that we use in ML model. Financial modeling. Identify hidden market regimes and trends within stock price, movement and trading data. Bioinformatics. Analyze and predict gene sequence, protein structures, and biological patterns. Activity recognition. Understand and predict user behavior patterns from accelerometer and sensor data. For handwriting recognition. Convert pen stroke sequence into text by modeling the temporal dynamic of writing. Final when with summary and keywords will explain. So structure interface. HMM, that means hidden Markov model, provides a mathematically visual framework for interfering hidden state from observable sequential data. Practical weather prediction. This weather model demonstrates core hidden Markov model principles applicable to real world forecasting challenges. Extensibility. Simple model scale effectively, adding more state observations or incorporating real meteorological data sets increases accuracy without fundamentally changing the approach. Broader impact. The probability foundations of hidden Markov model unlock solution across peace, genetic, finance, human-computer interaction, making them essential tool in modern data science. Thank you.